This is Ruibing Chen, and this video shows my solution to question 1 of homework 10. The question 1 asks us to collect the definitions and the simple properties of the following examples of stochastic process. Firstly, let's focus on the Poisson process. The Poisson process, its definition defines that for a process it's x0 is equal to 0 and xt1 minus xt2 is equals to the number of calls received in interval t1 to t2, and the number is followed with the probability xt1 minus xt2 equals to k. K is the number, and it is equals to e of the power of minus lambda t1 minus t2 times lambda t1 minus t2 up to the power of k divided by k scale. And for the properties of the Poisson process, the probability density function is equals to p. The probability of xt1 minus xt2 equals to k is equals to e of the power of minus lambda t1 minus t2 times lambda times t1 minus t2 to the power of k divided by k factorial. And the mean value, the expected value of t is equals to lambda t. The autocorrelation RT1 T2 is equals to expected value of xt1 xt2, which is equals to lambda squared times t1 t2 plus lambda times minimum of the t1 and t2. The auto-variance is equals to autocorrelation minus mean of the t1 and times mean of t2, so it is equals to lambda times minimum of the t1 and t2. Secondly, let's turn to the Poisson increments. Poisson increments is defined that with xt is a Poisson process defined before, and for epsilon, for a positive epsilon, a given constant, the Poisson increment is constructed by yt equals to xt plus epsilon minus xt divided by epsilon. The properties of the Poisson increments are as follows. Firstly, the probability density function. The probability of the yt equals to n divided by epsilon is equals to e to the power of minus lambda epsilon times the lambda epsilon to the power of n divided by factorial of n. The n here is the number of the arrival in the interval, which is similar as the k in the previous definition. The expected value, the mean value of the Poisson increments is equals to expected value of yt, which is equals to this. So, and we can move the 1 divided by epsilon out of the expected value. So it is equal to this formula. And we can get, because xt is a Poisson process, so it is equal, the expected value of it is equals to lambda times epsilon. So finally, the expected value of Poisson increments is equals to lambda. Similarly, the autocorrelation of T1 and T2 is equals to lambda square if the absolute value of T1 minus T2 is greater than or equals to epsilon, or the value is equals to the R is equals to lambda square plus lambda divided by epsilon minus lambda times absolute value of T1 minus T2 divided by epsilon square under the condition when T1 minus T2, the absolute value, is less than epsilon. The autovariance is equals to 0 when the absolute value of T1 minus T2 is greater than or equals to epsilon, and or when absolute value of T1 minus T2 is less than epsilon, it is equals to lambda divided by epsilon minus lambda times absolute value of T1 minus T2 divided by epsilon square. Thirdly, let's consider the Poisson impulses. The Poisson impulses process is defined as the zt equals to dxt divided by dt, where xt is a Poisson process. Its figure is like this. By the definition, we can see that the Poisson impulses process does not have the probability masses. The probability masses function is not defined. And the expected value, the mean value of the Poisson impulses is equals to lambda. The autocorrelation RT1, T2 is equals to lambda square of the lambda plus lambda times impulsive of T1 minus T2. The autocovariance CT1 T2 is equals to lambda of the impulsive T1 minus T2. Fourth, let's turn to the semi-random telegraph signal. For a semi-random telegraph signal xt is defined based on the Poisson process, and it is defined that for the number of the points in the interval T1 and T1 to the T2, with length t is also, if the points number k is even in 0 to t, xt is equals to 1. Else, if k is odd in 0 to t, xt is equals to minus 1, where pk, the probability of k number, is equals to e to the power of minus lambda t times lambda t to the power of k divided by factorial of k. We can see that the probability methods of xt equals to 1 is equals to the sum of all the probability that k equals to even. K is even. Therefore, it is equals to e to the power of minus lambda t times the cosine hypologic lambda t. Similarly, the probability that xt equals to minus 1 is the sum of all the probability that k is odd. It is equals to e to the power of the minus lambda t times sine hypologic of lambda t. And its expected value mean eta t is equals to 1 times the probability of xt equals to 1 plus minus 1 times probability xt equals to minus 1. Hence, it is equals to e to the power of minus lambda t cosine hypologic lambda t minus e to the power of lambda t times sine hypologic lambda t. The final result is e to the power of 2 lambda t. The autocorrelance is equals to e to the power of minus 2 lambda times absolute value of t1 minus t2. The autocovariance is equals to e to the minus 2 lambda 2 times absolute value of t1 minus t2 minus e to the power of minus 2 lambda times t1 plus t2. Next, consider the random telegraph signal. The definition shows that we let alpha be a random variable independent of xt with probability of alpha equals to 1 equals to probability of alpha equals to minus 1 equals to, they are both 1/2 equals to 1 divided by 2, the half. And we form the process yt is equals to alpha times xt. The probability methods function of the random telegraph signal is equals to probability of yt equals to 1 is equals to probability that yt equals to minus 1. They are both same as 1 divided by 2. The expected value is 0 and the autocorrelation is equals to e to the power of minus 2 lambda times absolute value of t1 minus t2, and the autocovariance is equals to e to the power of minus 2 lambda times absolute value of t1 minus t2. Next, let's collect the definition and properties of the random walk. The random walk is defined as tossing a fair coin n times, Let k be the number of heads in the entoses, and we can get that the nt is equals to ks minus n minus k times s, which is finally get the 2k minus n times s. The xt is equals to we let xt equals to xnt for all nt less than or equals to t less than n plus 1 times t. For the random walk, the probability method is defined as the probability that xnt equals to rs. And it is finally equals to this formula. The expected value of the random walk to get this expected value, we need to construct a new variable. So we construct that for yi, a new variable. The yi is equals to s if the result is head, and minus s if the result is tail. So the xnt is equals to the sum of all yi, and the expected value of yi is equal to 0. So the expected value of the expected value of xnt is equals to expected value of sum of the yi, and it is equals to the sum of expected value of the yi, so it is equals to 0. The autocorrelation is equals to expected value of xt1 times xt2, which is equals to expected value of xnt times expected value times xmt. So it is equals to minimum of n and m times square of s squared. The autocovariance C(T1, T2) is equals to minimum of n and m times s squared. Finally, let's see the Wiener process. The Wiener process is defined as a limiting process of random walk, where the Wt is equals to limit that t is close to 0, n is close to positive infinity, and s squared divided by t is close to alpha, a constant. The limit of the xt. Then let's consider the density function. To find the density function, we first calculate the distribution function of the Wiener process, which is equal to probability that Wt less than or equals to W. And it is equals to limit of xt is less than or equals to W, which is also limit equals to limit of probability xt less than or equals to W. Therefore, the distribution function is equals to half plus the error function of the W divided by square root of alpha t. Therefore, we can calculate the density function of the Wiener process. Fw Wt is equals to 1 divided by 2 the square root of 2 pi alpha times t times e to the power of minus w squared divided by 2 alpha t. The expected value is simple. It is equal to 0, and the autocorrelation is equal is equals to limited expected value of Rx T1 and T2, and it is equal to limited expected value of xnt times xmt. So it is equal to limited of the mean n minimum of n and m times square s square, and finally it is equals to minimum of T1 and T2 times alpha. The autocovariance CT1 and T2 is equals to minimum of T1 and T2 times alpha.